going back. Go ahead. Where is the paint? Mahi, come on, read the question.
What is the nearest worst case upper bound to search for the largest element in the sorted array and in a binary search tree, respectively? Okay, the worst case.
Okay, sorted array and binary search tree, right? So let's say we have like sorted array 1, 2, 3, 4, 5, and 6.
For
Right?
binary search tree.
Now this is for sorted array. Sorted array. What's the find the largest element. What's the order?
It's n.
N or 1?
Sorted. Okay, it's 1.
Because you can directly take the last
for
element.
binary
Right?
search tree, it's n. For binary search tree, it's n because we have to get for the worst case, and worst case is like a total array, so it's n.
You're right. So for binary search tree, it will look like this, right?
Yeah.
So 1, 2, 3, 4, 5, 6.
No, sir, please explain what is binary search tree, because I'm not able to get how you make it linear.
Okay. So binary search tree is something where so you have the middle element at the thing. The left element will be lower than this node, and the right element will be bigger than this.
Okay. So we can have one node also.
We can have. Sorry.
There's no compulsion that the previous node should be filled, something like that.
No, that is for heap.
Okay.
You should know the difference.
Thank you, sir.
Okay, good. Okay, if that is troubling, so just for the concepts alone, we'll come here, right? So I think we are looking at week 6, huh? Yeah. This is not thing. All these are code. I think nothing is here.
So here also I have a doubt that heapify function, it's written big of n. I also have a doubt there.
We'll first finish this, Ravina. Okay. Are you guys okay with this? Like why it is big of n to find out the biggest element?
Big of n is okay, but why 1 and?
Why 1? Because see, it's a sorted array, right?
Okay.
Which
so
means
we have to iterate now.
No, which means
the large element will be the largest element. That's why
always it will be the largest element.
Yeah,
right?
-1. If you take a of -1, that will give the error. So it is just the order.
That's why.
Okay.
Got it?
Yeah.
Good. Anyone else want to ask something here in this for this question? Okay. So this question.
So the worst case in binary search tree is always either left skewed or right skewed, right?
Correct.
That will be the only way. Otherwise, it will be always log n.
Yes.
In normal case situation.
Correct. Good. Yeah, Uma, this question is for you.
Given code is the incorrect implementation of Minheap. Which of the following lines of code, if replaced for the given line number, will correct the above code?
Okay. So, Minheap, right? So let's do one thing. Let's try to run this code. Like how do we do this?
I'm getting the question first of all.
Okay. The question is saying that so line number 9 and 11 is incorrect. Okay. So if you're replacing that line 9 and 11 with this number, these two codes, then it will give us the correct Minheap.
Okay.
See, given the incorrect implementation of the Minheap, which of the following lines of code, if replaced for the given line number, will correct the above code?
Yeah.
Okay. So yeah. So they all, it looks like until line number 9, everything is fine, right? Because we don't have anything before 9. Am I right, Uma?
Yeah.
So let's read until line number 9. So
okay,
I think we should start from line number 13. This is where the implementation is coming from.
Yeah, define build Minheap of array A.
Yeah.
N is equal to int of len of A by 2 minus 1. Like actually, we are dividing the list into half, right?
Correct.
So the iteration goes on up to the half of the list, right? Am I right? Because the n
No.
is equal to half, right?
Let's calculate also. What do you say? Let's take an example array. 2, 3, 8, 5, 4. This is fine.
Yeah.
So what is n? N equal to?
N is 2 must be right.
Oh, what is that going to be?
Oh.
5 double bar 2.
6 element, right? It will be little.
2 minus 1.
You can take 6 elements. It will be.
Okay, you want me to take 6 elements? Okay.
Yeah, so that will come as 2.
Then I'll take 6 here. Okay.
Yeah. So 3 by 2 will get minus equal to 2.
So 3 by 3 minus 1, which will become 2. So n will become 2. Am I right?
Yeah.
Okay. So for k in range of n comma minus 1 comma minus 1. So we'll start from 2, 1, 0. That's all. 3 iterations it will go. Right?
Yeah.
So sorry, Uma?
No, I'm just reading. Min heapify A comma Q.
A comma 2. Let's start with this.
Yeah.
Go ahead.
And n is equal to 2 into k plus 1. Left side, I think. This is the left side, right?
Yeah. So 2 into k plus 1. What is happening here? So this will be 5.
Yeah.
So this also will be 5. L is 5, R is 5.
Sir, I have a doubt. It's the child value or the index of that left child? I'm confused.
Repeat.
Sir, is it that left child or the index of that left child?
I'm not sure. Let's read the code and conclude it.
No, R is equal to not 5, right? It is plus 2.
Okay, plus 2 means 6, huh?
Yeah.
Okay.
Smallest is equal to k. So smallest is equal to 2. If L is less than len of A.
Okay, L is 5.
Yeah. Yeah. And A, L, right? It is.
Yeah, A of L. L is 5. The last element of A, which is 4.
Can you zoom a little bit? It's really small.
Okay. Okay.
Slightly, it is not zoomed. Okay, it's okay.
Please adjust, Uma, please.
L looks like, yeah. Okay, A of, that is L, right?
Yeah, A of L. And A of L is less than A of K.
Yeah.
So A of L is basically 4 here. Right?
Yeah. Yeah, it's less than A of 2, right?
A of 2, which is 8.
Yes, that is true.
That's correct.
The smallest is equal to L.
Okay, smallest will become now 5.
Yeah.
Okay.
And if R is less than len of A and A of R, now we have to go check for R.
No, R is not less than len of A, right? Because R is 6 here and len of A is 5. Sorry, len of A is also 6.
Yeah.
So this if condition is not satisfied. Right? So if
yeah.
Go ahead.
Smallest is equal to K. Yes, right? K is
Smallest equal to K. Smallest equal to K. In our case, K is 2 and the smallest value is 5.
Okay.
Right.
Yeah, it's not equal.
It's not. So we are removing this. So for the first iteration, this is what is happening. So smallest has become K. I mean, smallest has become, that's what is happening. There is nothing returned. Okay.
So we are swapping with A of Q and A of smallest.
Where are we swapping? No. We are not swapping, no?
Okay, if smallest equal to K. Okay, yeah, we will not go into this, right?
So we'll go again. So A comma 1. I think it's trying to find out the minimum most. There's a min heap, right? Okay, wait a minute. So
Sir,
there's
how 1 came, it should be a comma 5 now.
sorry.
No, we are starting over.
Repeat.
So it should be a comma 5
Why?
because smallest is 5.
No, here it is k. This is where we are at. Actually, Uma.
No, sir, but we changed the value of smallest is equal to L in the line 6. So it should be 5.
Here, yeah, smallest equal to 5. That's right. Okay. And in this case, 5 equal to 2. Is it true?
No, but value we have changed on. It should be 5.
K value has not changed.
Huh. And we are iterating over here. That k is different from this k.
Okay.
And one more thing, Uma, let's go for the right implementation.
Yeah.
Okay. So we'll take this for line number 9 and 11. Yeah. So I'm having line number 9 and 11 here. Go ahead. Now we are not supposed to read this. So now see this, Uma. If smallest,
If smallest not equal to k,
correct?
then we have to minheapify a comma smallest. So now it comes like minheapify a comma 5.
Good. Okay.
So then we have to go back. A comma 5.
So now L will become
2 to 5. 11, right?
yeah. A will become 11 and R will become 12. Okay. And K is 5. We have seen it here, right?
Yeah. So anyway, here it doesn't work out. L is not less than and R is not less than. They're not fair, right?
Yeah. These both are not right, not true,
Yeah,
correct?
so we will go down for this ninth line, right side, right?
Yeah.
If smallest not equal to k.
But smallest is equal to K, I think, right?
Yeah.
Smallest is 5.
So we
So
won't go inside.
we don't go there. So at the end we come back. That's all.
Come back to for loop, right?
Yeah, we are coming back to for loop. We are calling this function.
Okay.
And by the way, look, see, when A of 5 is happening, so we need to do these things. A of k comma A of smallest equal to A of smallest comma A of k. So we need to interchange.
Swap it, okay.
Correct. At that point, what was k? So smallest not equal to k. When we did, it was 5. Right, Uma?
Yeah, smallest should be 5, right? K
It was
must
5.
be
Correct.
2.
It was 5. And 5 we were interchanging it with 2. Right? And A became now, A now became 2, 3, sorry, 2, 3,
4.
it's 4, right? 4, 5, 6, 8. Now we have a new A here,
Okay.
right? And for this, we are calling the min heap 5 of A comma 5. Okay, so that means now see this. Anyhow, A of L is not there, right? Because A of 11, A of 12, it's not there.
Yeah.
So,
So we have to come back to 8, comma 1. That's what we did, right?
correct. But won't it throw, okay, so wait a minute, smallest equal to k, but won't it throw an error here at that point saying that list index out of range?
No, we won't go inside the if loop. It's a if loop, right?
Okay. So it won't go to this condition because L is less than
Yeah,
length of
L is
k.
not less than, yeah. So
Okay.
we will never enter this
So,
both
okay, got it now.
But I don't understand what we do with the K.
Which k, Uma?
No, what is K doing?
Which k?
No, A comma K, what is this K value is doing? I'm not getting the picture.
Line number 11. Okay, wait.
No,
This
no,
was
in the first line itself I'm asking.
Fourth one.
Heapify what? A comma array is heapified with what is the k value is doing?
I'm still wondering here.
So we are taking some random index value, is that so? From that point we are starting the heapify.
Actually, this k value is nothing but the minimum point, middle point. If you remember, see, yeah,
Two
n is the middle point, right? Middle place.
Okay.
So what I can feel is that so we
So we
have
start
6.
from the some middle point and then we started heapifying the structure, is that so?
Correct.
Because we didn't see the code heapify, right? We just saw heap and thing.
Hmm. See, for example, this is how at the end the heap is gonna come, right?
Yeah.
So for the 6 elements, right? So what we have done is basically, so for the min heap, okay. So where are we? We have this list, right? So n is basically saying that you start from the middle point.
Yeah.
Okay. So you see, you got 2, right? And 0, 1, 2, 3, 4, 5. So this is the length of the list. And length is
Yeah.
basically 6, and these are all the indices, right? You're trying to see whether the middle value is the lowest. It's a min heap, right? That means the minimum value should be at the top.
Oh, that way it's checking the root node, I think. That is where it is coming
Sorry,
from,
Uma?
right? And the 2 is what? It is element or index?
I'm just saying, like, no, I just put as index as of now because you're starting from 2.
Okay.
Okay, then you're passing in a comma 1. Now you have a heap which, I mean, array which looks like this, right?
Yeah.
Okay, now you are trying to a comma 1. For a comma 1, how will it look like? What will happen?
0, 1, right? It will not change because it is in.
Okay, now let's see this actually. 2, 3, 8, 5, 6, 4, right?
Yeah.
Okay,
Because 8 is greater than.
yeah. So this will change. These things will change. Now at the end, it will change to 4 comma 8, right?
Yeah.
Hmm. Because this is a bigger value.
Now again it will not change, right?
Sorry, Ma?
Now furthermore it will not change
Yeah,
because
further no
it is
change because this is a min heap.
yeah. So we should know actually the code, I think. Otherwise we can't answer such questions.
Correct, that's right.
It's very difficult. Yeah.
Hmm. Let's skip this as of now, Uma. What do you say? It's taking some time, right?
Yeah, let's move on because
If we move on, only we'll be able to complete this. Then we'll come back. So please just make a note of this, that we are supposed to do this question. All right, or else I'll do a record and give it to you guys on how to do that. Okay. So coming back.
Excuse me, sir.
Yeah, Ravina.
So that previous question.
Yes. This one.
No, sir. Okay, we can move on.
Sorry. Okay.
Yes, sir. We should discuss next question.
Okay. Fine. Mahi, or else anyone else is here? Charles. Hey, Charles, are you here?
So we don't have time for these questions, so we should discuss some coding question like the previous one which we discussed now.
It's not the case, Ravina. We have to deal with everyone, right?
Sir, you have already taken one session for only these questions, so you are repeating it again.
Now, what should I say for this? But it needs the concepts also, right? Hey, uh, instead I would say, like, let's finish this fast, Ravina. Okay. Apologize. So I need to take these questions here. Sorry. Mahi? Hello? Mahi, are you here? Am I audible?
Yes, sir.
Yeah, go ahead. So this min heap. So which of the following represents a min heap? So how do we do this?
It's like we should make a tree,
Very
heap
good.
tree.
Okay. Heap I should draw,
8,
right?
10, 12,
8, 10, 12.
25, 40,
Mhm.
17.
Yeah.
Yeah.
So does
So
this,
it's a min heap
how do you tell
because
that?
8 is smaller and 10 and 12 is bigger.
Mhm. Yeah, that's right.
And for same goes for,
Mhm.
and similarly for 3, 4, 5, 11, 9, and 6.
Yeah.
This is also a min heap because 3 is smaller than 4 and 5 and 11.
Yeah.
4 is smaller.
Basically, the parent is smaller than the children.
Yeah. And
Right.
same goes for the next one.
Okay. So I'll draw that also.
Okay.
Hey, anyone else here who can talk? I mean, Harish, Kishore. If you guys respond, we can give you the questions. So you can also try it out. Yeah, Mahi, is this a min heap?
No, it's not min heap because 25 is greater than 8.
Yeah, that's right.
Next one is okay.
So next one is 8, 10, 12, 25, 17, and 14. So again, here the parent is smaller than the child, right? So this is a min heap. Hey, is that clear for all?
Yeah.
Yeah. Charles, Nomit, Shibin, Kishar, any doubts in this?
Here. No, no.
No, sir.
Great.
No, sir.
Yeah, sure. We'll go to the next question. Okay. So this is an interesting question here. Okay. Do you guys remember pre-order, in-order, post-order, traversal of BST? By the way, let me take Nomit here. Hi, Nomit. It's been some time.
Hi. Yeah.
Okay. Do you remember what is binary search tree?
Yes.
Okay. What is a binary search tree?
It's like, uh, mm, I don't remember the definition. I remember it roughly.
Okay. Just tell me in your own words. More than enough.
So we have like a node, and the element on the right would be bigger than that, and the
Left will be
child on the
smaller
left.
than that.
Yes.
Exactly. You're right. Okay. So let me just take some example array. All right. So 5, 7, 10, 2, 3, 9, 8, 4, 1. Okay. So this is something here. All right. So, and if I want to construct a binary search tree for this, all right, how will I do that? Can you help me here?
Sure. So 5, then
Where
left
will
would
7
be
go?
7.
7 will go
Right.
towards the
Sorry.
right. Okay.
hmm
And since 10 is greater than 7 and it goes towards the right of 7, right?
Yes.
And next we have 2. Where should 2 go?
Left of 5.
Very good. So 2 should go to the left of 5. And where will 3 go?
Right of 2.
Very good. Right of 2 will have 3. All right. So where will 9 go?
Left of 10.
Left of 10. Very good. Because the left of 7 will be values which are less than 7. Yeah. Hey, just give me a second. Yeah. Go ahead. Where will 8 go?
Will go towards left of 9.
Very good. Okay. Tell me. 4.
Right of 3.
Okay. 1.
Left of 2.
Okay. So now we have a binary search tree here. Is everyone okay with this? How we have constructed? We have some new people also. Hi Janani, Kishore.
No, sir. No doubt.
All right, great. Shibin, I think everyone should be clear with this. Mahi also okay, right? Okay, fine. So there is something called as in-order, pre-order, post-order. Know it?
Yeah.
Okay. So
Mm-hmm.
okay, I'll show you with an example. Like what is an in-order? In-order, pre-order, post-order. So we'll take example here, and then we'll try to compute it there. Okay. So what is in-order is basically you'll start from the left, then goes the center, then goes the right. Okay, then again, so now that left node is covered, so you're going to cover up this 15, then again you come to the leftmost 18, 22, 24. Are you able to follow this?
Yes.
Yes.
Okay, so this is called as in order. So hope it, okay, I'll just copy this also there. So let's see, anyone else want to try this, how to do this in order? Who was answering? Shibin, were you answering?
No.
Okay. Yeah. Can you tell me now? Okay, let's ask Nomit. Nomit, tell me what is going to be the in order for this.
Mm. So 1,
Good.
2, 3,
1, 2, 3, and 4.
4.
Good. Yeah.
Uh, 5, 7, 10, 9, 8.
Great. Should it be you know yeah, okay, that's right. I mean 5, yeah, 7, then 8,
10.
9, 10.
Sorry.
Yeah. Okay. Good. So that's how we have got it here also, I think, right? 50, 66, 70, and 90. So do we have the code for this? In order, pre-order. I don't know if we have the code for that. Okay, fine. So hope you understood that in order, right? In order is nothing. Just we are taking it in order. Okay. So if you see, then in order is nothing but it's going to be in ascending order, right? You gave the array as a some random order, right, Shibin? Sorry, no, Nomit.
Yes,
Yeah.
yes.
Okay, we
Yes.
gave the array in some random order, and in order is
Mhm.
going to give us in ascending order. Simple,
Hmm.
right? Nice.
One second, Gokul. How we went from 5 other side? Here left diagram is a left parent and then right child, right?
Correct.
So again in the right also the same way. Left parent and
Yeah. So you don't have
so
any left on the 7, right?
yeah.
So left is covered. So then you go to the parent.
Okay.
Then you come towards the right. So like, you mean if you go to the right, you should go to the leftmost of the right.
Okay.
If you see, the same goes here. After 25, okay, you come toward the right
Left
and
and then parent and
leftmost.
then right. Yeah.
Yeah, you're right. So we cover up this first, then we go to 50, then we come to this part.
Okay. Thanks.
Great. Okay. So now that Naveen, I think you're clear with this. In order. In order is nothing but sorted. Okay. We have something called as pre-order. So what does pre-order look like for you? Can you explain looking at the picture? It's simple.
Like I remember from the lectures,
Mhm.
we mention the means we write the child node first and then the node in the middle, which
Look
the
at this.
parent node.
But we're talking about pre-order. I don't think it's child. See now the parent is coming up, the left. Okay. So then we
Oh,
cover up
yes.
with this part. So we start with parent, left, and then right.
Mm-hmm.
So now the left part of 15 is covered. Okay. So we start with the parent. Okay. So let's try to understand this. So we got 25. Okay. Then 15, 10, 4. This is okay. Right. After that, we are covering now that left parent and left is covered. We are going to cover the right one, which is 12. Okay, now we again go back to 15 here. So left part is covered and we come towards the right, so which means now we are covering up the parent. Okay, parent, left, and then right. Got the point?
Yes.
Okay, now the parent is covered. So here also, if you start, you should start with 50, right? 50,
Hmm.
35, 31, right? 50, 35, 31, right? Then you go here. I mean, you covered the left part, then you cover the right part. Parent, left, and the right. Okay, so now again after this, it will be 70. What is the left? 66, and then 90. Got it?
Yes.
Uma,
Yes.
Shibin, Mahi?
Yeah.
Oh, okay, I understood.
Great. Okay. Would someone else like to try this out? Answer this now. Mahi, can you tell me what is going to be the pre-order for this? Okay. Shibin, can you try?
5,
Okay. So 5.
2, 5, 2, 1, 3, 4, and 7, 10, 9, 8.
Very good. That's all. See? Easy, right? Okay. Just make sure you remember this. All right. What order it is going to be. Pre-order means first comes the parent, then comes the left child, then comes the right child. Okay.
Okay.
But post-order is just the opposite of this. First comes the children, then comes the parent. So first comes the left child, then comes the right child, then comes the parent. See?
Okay.
Okay. So what I'm going to do is, now come on, someone tell me. So what is going to be the post order for this? What did I tell you? I mean, left child, right child, then the parent. Okay. Tell me what is going to be the parent for this. I mean, post order for this. Who want to try this? Janani, are you here? Kishar?
Yes.
Okay, wait. Kishar is saying something. Kishar, you want to try this?
4,
Okay,
12,
great.
10,
4.
12, 10.
Wait. Left, right, and parent.
Yes.
So 4, 12, and then 10.
12, 10.
Yeah. 4, 12,
Then
10.
15.
Good. So now the
Then
left is
15.
covered. No, wait a minute. Left is covered. So that means now you should cover the right. Then only you should go to the parent. So that means 18,
18,
24, 22.
22.
Right? So now this left is covered. This right is covered. Now we go to the parent. Now it is 15. Correct?
Sir.
Go ahead now. So we are coming to this side. So now the left part is covered. So if you come here, the leftmost is
31.
very good.
44.
44. Super.
68.
Where is 68? There is no such thing as 68. This is 35.
Oh, sorry, sir. 35.
Yeah, 35.
Then 66.
Good. Because why? Because you need to go towards the right side and then the leftmost of it. Yeah, 66.
90.
Very good.
Then 70.
70. Very good.
Then 50.
50. Finally.
Then 25.
Okay. So let's verify this. Even I don't know if we have done it right. Okay. Here we are. 4, 12, 10, 18, 24, 22, 15, 31, 44, 35, 66, 90, 70, 50, 25. Awesome. Bro, you rocked it. You got it correct. Okay? Kishore, happy?
Yeah.
Okay. So Janani, come on. You can try the same thing for this one, our graph. The post order.
Okay. 1.
Left, right, and then parent, right?
Okay.
Okay. Yeah.
So it's 1,
1.
3, 4.
Actually, left, right, and parent. Okay. For this also, you don't have a left here, right?
Oh,
Means
okay.
it's blank. So you should cover the rightmost of this, then you come to the parent.
Fine. So 1, 4, 3,
Very good.
2,
2.
7.
Yeah, that's right. Wait a minute. How come 7? You have.
Okay, 7 won't come. So there is no left, so it will shift to right. So it will have 8, 9, 10, 7, and 5.
Very good. 8, 9, 10, 7,
7,
and 5.
5.
Very good. So this is our post order. So is everyone okay with this in order, pre order, and post order?
Yes.
Okay.
Yes.
Give me a second. I think I'll close the door and come. Go back. Ha. Yeah. Fine. So I'll also give you guys. Now let's go to the question. Now that everyone will know what is pre-order, post-order, and in order, let's come to this question. I'm gonna delete this. I'm gonna put it here. Yeah. Who is gonna answer this? Janani, come on, answer this question. Hey, wait a minute. Mahi, are you here?
Yes, sir.
Why are you silent? Then you answer this question. You were so silent. I'm giving you a punishment.
Mm,
What is this in order traversal?
that we did just now.
Right. So it will be sorted. Correct? Hello? It's a sorted order. In order is nothing but the sorted one, right? So if you're given this, so will we be able to construct back the you know the tree? Let's try it now, guys. Why don't we try that? I'm gonna take this. Okay, just these graph. We have the three ordered things. Okay, Mahi. So shall we try to reconstruct the tree? Hmm?
Okay.
Okay. How do I do that?
So for in order, what's the condition?
So left parent
Left,
and then
right.
right.
Okay.
4.
So 4 and then parent 10, then right 12, and this become our left. Then we go to parent 15, 10 to the top 15, and then it's parent, then right 18, the right 18.
Is this correct? I'm not sure. Okay.
Okay.
If anyone feels incorrect, please tell me.
Right. Okay. So,
Go ahead. Hey, let's go ahead with your way. Then we'll find out where we are making mistake. Even I'll make mistake. If you ask me to do, I'm gonna do the same.
so left parent and right.
Seems like we have 22 here, right? So we are supposed to write it here, I think. So probably we don't have anything on this left. Okay. So if you are so much confused, I'll draw this also. Yeah. Now that we have the graph also. Okay. Go ahead, Mahi. So let's see how we are constructing it back. 4, 10, 12, we are fine. Then we got 15 here, right?
And then 18.
Then we made a mistake of, so 18 should come here.
Yeah, 18 should come here. 18, 22, and 24.
So 18 comes here.
But how can we say that there always be 3, 1?
Exactly. That we will check it. Okay. We'll
Okay.
verify it. We'll verify it.
Okay. Then this is our left, and then we go to 25. That is the top of 15. And then 31. I guess 31, 35. 31 should be there.
Sorry.
So working instead of doing this, we are unable to do. So we need the root node. Only then we can construct the binary search tree, right?
Okay.
So in Inorder traversal, we don't know what is the root, right?
Yeah.
So we can't do with the in-order traversal. But for pre-order and post-order, if you look at it, the root are at the both end. So that is a clue for this question.
Okay,
And
that's the
I
clue
don't
here.
answer correctly, but pre-order and post-order, we have the root node, we can go.
Hmm?
But in-order, we don't know the root node. That is why we are stuck in between. We can't.
Correct. Okay.
I think we need a pair. I'm not very sure about the answer.
The pair I'll tell you. I mean, you're asking about the last option, right?
No, I don't know the answer, but the thing is, both post and pre-order, we have the root node.
Correct. So Mahi, as you guessed it correctly, right? So we were not able to do it. Even I was also not able to do it, right? With in order. Okay. Just with one order, in order, we are not able to do it. But with pre-order, shall we try? So what is pre-order? Mahi, pre-order is parent,
Left, right, parent.
parent, left, right. Okay. So that's
25 is parent
mm-hmm.
and 15 at the left
Okay.
and 10 at the left
Since
of
10
15.
is less than 15, right? We go left. And then 4 is less, we go towards the left. Got it?
Okay.
Now, after 4, we have 12.
So 12.
So since it's increasing again, so we go here and put 12. Okay.
And then 15 above.
15 is here.
22.
Now, if we have 22. So if we had 13, we would have put it here only. Right. Fine.
Okay.
So we go here and put 18.
No, 22.
Achha, wait a minute. Why 22?
22. It's 12 and then 22.
Achha, here we are. Like, I'm sorry, I was looking at this. Let me just close it. 12 and then 22.
22. And 18.
18 on the
And
left.
at the left of 22.
Mm-hmm.
Then
18,
24.
24. Right? So now we'll be able to construct it again. Okay, let me. Okay, come on, finish it up fast.
50 and left of 50, 35. And left of 35, 31. And then 35. Right, I guess 44.
Now we are making some mistake. I mean, the 35 should not come here, right? 35 we have put there.
35 right, it's 44.
Correct. Then?
And then 50, 70.
Yeah.
Okay. And
left is 66.
Left is 66, 90.
So basically, it's parent, left, and right. Correct. So with the pre-order, we are able to get back the tree. Okay. Nomit, fine. Shibin, Kishore,
Yeah.
any doubts?
Can you repeat it?
Kishore,
Hello?
tell me.
Can you repeat it? How to construct this from pre-order?
Bro, it's parent, left, and right. Okay. So you have the parent, which is 25. You're writing it first. Okay.
Okay.
Then 15 is going to be on the left of that. Okay. Since 10 is less than 15, it is going to be again left of that. Okay. Now 4 is less than 10, again left of it. Okay. See, this many things are going to come on the single line. Now after 4, it is increasing again, right? So which is 12. That means 12 is supposed to come after 10, right? It can't go on the right of 15. Yes or no?
Yes, yes. 10 is greater than 12.
Correct.
12
10
is
is less
greater
than
than
12.
12.
Yeah.
Yes.
So we put it here. Now we have 22. Since 22 is greater than 12 and it's greater than 15 also, you go towards the right of that, which is the parent. Then you have 18, which is left, and 24 on the right. So basically, you can draw this by yourself. Got it?
Okay. Okay. Got it.
Yeah. So that's how pre-order and post-order. Shall we try to do the post-order also? Or is it okay for you guys? Mahi, Uma?
No, we can move on. We can try because we can cover a lot of questions.
Yeah. So, and that's right. We'll move ahead. And Uma, as you told.
One point is the pre-order I want to add. because the 25 is a root node, it is easy to construct.
Correct.
The first node is the parent root node, actually, in pre-order.
In pre-order.
And
That's
the last node is the parent node.
very good.
Root node.
Yeah. Mahi, okay?
Yeah.
Given the pre-order and post-order, if they are asking you to find out, tell what is going to be the root node, then you should be able to answer. Pre-order is going to be the first one, and post-order is going to be the last one. All right? Yeah. Tell Mahi.
There is the question graded assignment 11th question in which we have to convert pre-order to post-order.
We'll do that question now first right away. Okay? Yeah. Uma, shall we cover this?
Yeah, I don't know whether I can answer.
So, yeah. They are given us the pre-order. So how do we convert it to post-order?
Pre-order traversal binary search tree is given. Which one of the following is the post-order traversal of the binary search tree?
So from the pre-order, we shall construct the binary search tree, right?
Yeah.
So shall we construct it, please?
Yeah, 15.
15.
And left is 10.
Yeah, we just saw it, right? We just saw it how to do this.
Yeah.
Right?
Right is 12.
Good.
Then again.
We have 11, which means it will come towards the left of 12, right?
Then right of 12 is 20.
Not right of 12.
Sorry, right of 15, 20.
Mm-hmm.
The left of 20 is 18.
16.
16.
19 will be here.
19.
Okay. So this is how the graph is. Now for this graph, we are supposed to write the post order. So what is post order? Post order is
right parent, right?
Correct. So left we don't have anything here, and right we are trying to cover. And we should start from 11, right?
Yeah, 11. We don't have any rights, so 12.
Mm-hmm.
And
so the left is covered, right is covered. Now we go to the parent, which is 10.
Parent. 10.
Now left is
then
covered.
Come to the other side.
Correct.
Come with 16.
Very good. 16.
19, 18.
19, 18.
20, 15.
20, 15. Right? So let's check that 11, 12, 10, 16, 19, 18, 20, 15. Correct. So is everyone clear with this? I think, who was that? Kishar, you were asking, you came to ask this question, I believe, right?
No, Mahi, right?
No, Kishar started saying that week 6, 11 question. So
Yes,
are you
I
clear
asked
with
this.
it now?
Yes.
Okay, so we beat any order. So if it is given as post order also, you'll be able to convert it to pre-order and do a rest of things, right?
Okay.
Great. Nomit, Ashibin, any questions?
No.
Okay, great. So that's 11th question is done. So we'll not look into coding questions. Uma, shall we cover up the theory questions? I mean, then we'll go to the coding. What do you say? Because coding is going to take so much time.
Yeah, we can do it.
Okay. Yeah. So then I'll come up again from the first. If it is required, we'll see that. Okay. Consider a list L with k distinct numbers and a heap H with size n. What is the nearest upper bound for checking if every number in L is present in the heap? So how do we do this? Who can try to answer this? Just try. So we have a list, okay, and they are saying that we have distinct numbers 1, 2, 5, 7, 8, 10. All right. Okay. So I'm gonna put 18 here, 15 here. So it's not in order. Okay. K distinct numbers and a heap H with size n. Okay. What is the nearest? Okay. Are they converting this list into a heap? Every number L is present in the heap. Okay. I don't think so because see they have some other heap. It could be anything. 1, 2, 3, 4. I'm just drawing something, okay? 6 and 7. So this is a heap, right? This looks like a heap, ideally, right? So how would you check if every number in L is present in the heap? So first we take 1 and we are trying to find out whether that 1 is present in the heap. How do we do that, Uma?
Yeah, so for every element we are we are going to n, right?
Correct.
So it will be k into n.
Huh.
Size of the list into n.
Correct. So where is k here? What is k here? Okay, k. Yeah, k is the length
Size of
listing
n,
numbers.
right?
Uh-huh. So k is length of the list, right?
Yeah, that is k,
Correct.
and
And
heap
n is
size
the
is n. So
size of
every
heap.
element in n, we are checking for n elements in heap, right?
Correct. So basically, the thing is, if we want to search for an element, so in this heap, we need to look into the whole thing, right? So that one can be, I mean, if we say that there is another element which is, 0, we can insert 0 here also, right? And -1 here also. This is just a heap. We should come in the order. That's all, right, Uma?
Yeah, I'm just thinking, I have a slight doubt
Tell me.
because usually say the heap height is log k, right? So is that any?
Heap height is log k, but the problem is this is just a heap. This is not a min heap or max heap.
Okay, maybe it is in the form of list also, I think, right? Heap might be present in the form of list.
Correct.
Only then n, k, n will be coming.
Hmm. So
Okay.
it's not required. It's not necessary that it has to be in a particular order, right?
Okay.
Mhm. So what if the element is not there in the none of the element is there in the heap? How will you search it? Basically, you need to search it 1, 2, 3, 4, 5, 6. Every element you need to search.
Element, yeah. Yeah, yeah.
So that's
So
why it is
investigate.
k into n. Mahi, did you understand or are you having any doubt? I think you are having some doubt.
For heap, I think it's necessary to be in tray order, no?
It's
It
tree
can't be
order.
linear.
That's correct. It's tree
Yeah,
order. Okay.
it can't be linear. So why not log in?
It can't be linear. Okay, Mahi. Now see, I'm gonna give 101, 10, I mean 102, 103. This is the list. Okay. Hmm? And heap we have 1, 2, 3, 4, and 5. So this is the heap. Now I'm asking you, in order to find whether 101 is present in this heap, okay, how will you tell that? So this could be that
I
heap could be
will.
in the any order, right? So it could be like 21. It could be again 13, right? Yes or no? It could be in any order. Heap could be in any order, right?
Yeah,
The
yeah.
values. So you have to check in. You have to look into all these elements, right? Every single
Yeah.
element. Then only you will be able to tell whether 101 is present in the heap or not.
Okay, okay, yeah.
Okay.
Got
Only
it.
the structure is like this, but you know this it has to go and search
Yeah,
all the
got it.
elements. Got it? Yeah. So if it was a min heap, okay. Should I go explain about that or should we go to the next question? Okay. Let me not take a different
Does
one.
it matter if it is a min heap or max heap?
Min heap. So Uma, take these values. Okay. So min heap will have the minimum value at the top, right?
Yeah,
So that means the parent is always going to be lower than the children,
yeah,
right? So that means, see, in this case, it'll 14 will come here, right?
yeah.
Okay. So 21 probably can be anywhere, not a problem, right? And 13. Okay. So if you're searching for the worst case is going to be the I mean so if you're searching for 101, okay, so you see these two, okay, and I'm not sure, like I think it's still going to be the same, right?
No, you won't be correct. At least in max heap, right?
Huh, in max heap.
Not in max heap if you check the root element. But I don't know
So
what.
let's draw the max heap for this. Okay, it'll be 50. Okay,
If
so
you
then,
check the root, it will be enough, right?
yeah, sorry.
No, no, anyway, it doesn't matter because they won't give a high. We don't know about the list, no? So it's
Correct.
fine.
Hmm.
I think it doesn't matter.
It doesn't matter.
Yeah.
Let's go further. Yeah. So identify the below arrays as min heap, max heap, or none. So who would do this? Who would like to do this? Whether this is a min heap or max heap or none. Amit?
Yeah. we can construct the heap and then check
Correct.
whether the elements are.
Good. So how do we construct it? Just 1, 2, 3, 4, 5, 6, 7, 8. So we can see that the parent is always smaller than the children, right? Hence it's a Minheap. I hope it's okay for everyone. So this is okay, right? I think you guys will be able to answer these questions. I'm gonna skip these. Shall I? Or anyone want to answer, see this? Okay, I'm skipping these questions. Which of the following will currently represent the Max-Heap? So shall I skip all these things, Uma?
You can ask others because there are many people.
Yeah, new people. What do you guys say? Like they are silent. That's the problem. Shibin, Nomit.
You can move forward.
Mm-hmm. Fine. Uma, which question you wanted to answer? You want to see which of the following will currently represent a max heap after inserting elements 1, 2, 3, 5, 7, 6, 4. This one was interesting, right? On that day. Yeah. I mean, you will be able to answer these and all, right? Min heap or max heap. That's okay.
Yeah.
Those should be easy. Right. So we come here. Okay. Which of the following will correctly represent the max heap after inserting the elements blah 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 in the given order, starting with an empty heap. So we have to construct a max heap for this. Yeah, Uma? So start with 1, insert 2. Since 2 is bigger than 1, we need to change it, right? 2 and 1. Okay.
Insert
So
3.
then we insert 3. Since 3 is greater,
Yeah.
yeah, this will be like 3 goes
3.
here. So we'll interchange 3 and 2,
Yeah.
right? So 3, 1 and 2 will come here. So next we are going to insert 5.
5.
So 5 is greater than all these things.
Tap twice, so 5 will come to the top.
Yeah, we swap it here, then this goes up and it comes here, right?
So it is like
So this is going to be like 5,
5, 3,
3, 1,
1, and 2.
and 2 will be on the right of 5, correct?
Yeah.
Okay. So then we insert 7.
7.
Mm-hmm. So since 7 is greater than 3, we swap, right? So now 7 will be greater than 5. So swap. Okay. So now this will come to 7.
5.
Mhm.
2. Other side.
Yeah, 2 on the other side. Okay.
1 and
1. And here
3.
it will be 3. Good. So next we are going to insert what? 7 we inserted. Then we have 6. So we are inserting 6 on the left. Okay. So 6 is greater than 2, right?
6.
Yeah. So now this will go here, and we don't need to interchange 7 and 6. So 6 will remain here, right? And 2 will come towards the left of this, right? And 5 is here, and 1, 3. Is everyone able to follow so far, guys? Shibin, Nomit, Kishar, any doubts?
Yes, yes. No, no doubt.
Okay. If anyone is not able to understand, tell immediately. Okay. Yeah, Uma. So I think people are following. So then we need to insert 4. 4 will be inserted here. Since 4 is not greater than 6, it remains there itself, right?
Yeah.
Okay. So now this, we should write it as a list, right? So 7, 5, 6, 1, 3, 2, 4. Yeah, 7, 5, 6, 1, 3, 2, 4. Correct. All right.
Yeah.
Yeah. Great. So this is how the answer is. On that day we took some time, but now we finished it fast. Yeah. Okay. So 8th question. What is the nearest? Oh, sorry for that. Let it be there. No problem. Yeah. Who want to answer this? Shibin, come on, try this. Just try this. Let's try. Just read the question. Read it loud.
What is the nearest? Actually, it's not clear.
The picture is not clear.
Yeah.
Fine. Shubin, is it okay? Okay, let me read this. Okay, what is the nearest worst case upper bound? Sorry.
Yeah, I'm able to read it. Bound to search for an element in a heap and in a binary search tree, respectively.
Hmm.
Total number of elements are.
Hmm. So searching an element in a heap and a binary search tree, right?
Yes, yes.
Okay. So let's take an example. Okay. L equal to 1, 5, 8, 2, 6, 3. Okay, that's all. So I'm gonna draw this as a heap. Okay, 1, 5, 8, 2, 6, and 3. So this is the heap, and let me draw the binary search tree also. 1 will come here, 5 on the right, 8 will come on. I mean, like, people should, you guys should be able to follow what I'm doing, right?
Yes.
Okay, 2 comes here. Then we have 6, which will be on the left of 8, correct? And then 3 will be on the right of. Yeah.
We should take worst case na in descending order or ascending.
Yeah, it should be either right skewed or left skewed. That is the worst case for binary search
Acha,
tree.
okay. So you want to take like that. Okay, sorry for the trouble. And
Think
if,
that's okay. We know the answer, so it's fine.
yeah. So if that is the case, okay.
So heap will be log n.
Tell me, Uma. Go ahead.
No, it's okay. Heap, I'm just telling the answer. Heap.
Okay, you're saying that heap is going to be what?
Log n, right?
Why? In heap, searching for any element is always n times, right? Hello.
I thought binary search worst case will be n, right?
So in this, if it is in sorted order, okay. Yeah, Uma. Repeat. Binary search tree.
Binary search, this is the worst case, right? So
What is the
there
worst?
is log of n.
What do you mean? Binary search. This is the worst case. That's true. Correct. I mean, this is the worst case structure, but finding an element is like finding an element which is not present in the list. That is the worst case.
Okay.
Wait, I'll just draw this also. Okay, 4, 5, and 6. So this is the binary search tree, right? Binary search tree for this list, and this is the heap. Okay. Anyhow, for heap, so and the question is to find 100. Okay.
Okay.
So in order to find 100, so how do you find it here? So in a heap, anyhow, you need to search everywhere, right?
Yeah.
So in binary search tree also, you have to search it, I think. But why have they given it as login? Can you guys check the answer in your place also?
Yeah.
It says nearest to a worst case, right?
Okay, that's right. So it's nearest worst case. So probably that's the reason. It's not the worst case. It's the nearest worst case. Guys, hello.
Yeah, what do you mean near worst case? We should not consider as a worst case.
Yeah, exactly. This is nearest worst case, which is not the worst case, right? So be it any case, okay, there is no best case or worst case for a heap. Yes or no, Uma?
Yeah.
Okay. So since there is nothing like that for heap, uh, so it's going to be n, always n for heap, right? And for binary search tree, it's gonna change, right? Am I making sense here, or what's the doubt here? Hello.
We saw no the initial worst case of binary search is n, right?
Yeah.
Which is
So
correct.
so they have given it as nearest worst case, so not the exact worst case.
Okay.
Okay. Is it okay, Uma?
And still not okay. Binary search is log n, then why not heap also? I'm still not getting it.
Heap. Okay, this is the heap structure. Okay, so let's
Yeah.
take the previous example. Okay, like I was having now 2, 3, 1, 4, 5, and 7. Okay, so this is the thing. So if I draw a heap for this, 2, 3, 1, 4, 5, 7, right? So this is how the heap is going to look like. Am I right or wrong?
Yeah, yeah. So we're going to search element n, right?
Wait a minute. So this is how it is, and let me just draw the binary search tree for this also. Okay, 3 goes towards the right, and 1 goes towards the left, and 4 goes towards the right, and then 5 and 7 will be on the right and right. Okay, so this is the binary search tree. Okay,
Yeah,
the question is to find 100. Okay,
yeah.
Uma, if you want to
Okay.
find, you
Yeah,
got
I
it, Uma?
got it. Because we are skipping the left side, no,
Correct.
completely. That
For binary
yeah,
search tree,
yeah.
you are skipping the left side completely.
We always skip the half of the binary tree.
Correct.
Yeah,
So all
that's
these
it.
things will be left. You just need to explore the right hand side, right most.
Yeah,
Right?
yeah, got it.
Great.
But heap we have to traverse through completely.
Everything. Okay, is that
Okay.
clear?
Yeah, yeah,
For all, Mahi, Kishore, okay?
Yeah, it is clear.
All right, great. So I think we are done with the eighth question also. What about the previous question? Previous question is also done, I think. So I am ignoring the coding questions as of now, Uma, because it will take time, too much time to revise.
yeah.
Okay. Now consider that value. Okay, let's do this also. Max heap is represented as an array. Now consider that value 25 is inserted into this heap. After insertion, the new heap will be. This is easy. Like let's do it fast. Okay, anyone can do this. Okay, how do we do this? First, construct the heap, right? Come on, guys. 40, 30, 18, 20, 15. Correct me if I'm making a mistake, all right? Yeah. So I think this is satisfying the condition for the max heap. Okay. Now they are saying that 25 is inserted. Okay. So now we need to insert 25 here. Am I right, Uma?
Yeah.
Okay. So now the 25 is, you know,
Greater than 15.
these two gets interchanged, right?
Yeah.
So and the structure will look like, I just put it 25 here and 15 here. Okay.
Yeah.
So and if you write it as a list, 40, 30, 18. Uma, go ahead.
Yeah, 20, 15,
No,
16,
it's not
17.
15. It's 25, right? Now we changed it to
25, 16, 17, 10, 4, 15.
4, 15. Okay, let's check it here with the answer. 40, 30, 18, 20, 25, 16, 17, 10, 4, and 15. That's correct. Is that okay for all? Nomit? Kishore? Mahi?
Yes.
Yes.
Alright, great.
Yes, sir.
Mhm. Fine. So that's done. This 11th question we have already done. Okay. I'm ignoring this 12th question. Okay. If you have time, we'll do that. Consider a heap H. Okay, this question we'll try to do it. Okay. Go ahead, guys. Someone read the question now. Nomit, read the question.
Consider a heap h with n elements and height h. The time complexity to update a value in the heap h is a function of dash.
Okay. So update the value in the heap. Okay. Oh, why is this like H and log n? Why is there two? Why is it MSQ? Okay. Okay, fine. Yeah. Log n is nothing but that. Okay. Uh, fine. How do I answer this question here? Uma, did you understand why it is H and log n?
No, I'm not even getting the question first.
Array, the question is, so we are having a heap. Okay.
Yeah, with n elements and
N
height h.
elements and the height is H. So what is going to be the height? Height is nothing but what?
The levels, right? Number of.
Yeah, that's log n, na?
Yeah, log n. Yeah.
Yes or no? H is equal to log n for a heap
Yeah.
always, right? So time complexity to update a value in the heap is a function of. So we have the heap, like as usual, we'll have the heap, right? So if we want to delete this thing, delete is also an updation, right? So if you want to delete this, all right, or else let's say that if we want to delete the root node, okay. So what we do, we used to put this here and take it here, and then we
Yeah.
remove this, right? So and then we do all the operations, right? So only we just look at the left and right.
Yeah.
Hmm? So it's the height of h log n operations. I mean, you got the point why I'm saying that?
Yeah. Yeah. Yeah.
Hmm. Okay, now I have a doubt. Okay, 1, 8, 7, 6, and 5. Okay, this is a heap. And if I want to remove the top element, what should I do? Hmm? Uma?
We'll we will put the 5 on the root.
Is it so? Is it how it is done? I mean, for min heap and max heap, it is done like that. Is it the same for the heap? Just normal heap?
Normal heap, we will update the nearest children. We just shift the children, right? Am I correct?
Okay.
I'm not sure. We just swap the because it depends on what heap is.
It depends on what heap. They're just saying it is heap, right? So that's why I'm getting confused here.
But anyway,
Sorry.
we have only two heap.
Sorry? Uma, what did you say?
No, anyway, we have either max heap or min heap, right?
Is it so? Don't we have a separate heap? Just a heap.
I don't know.
I think
Do
we
we?
have. We have it.
A normal heap would be a list only, right?
Okay.
I'm not sure what's heap
Yeah,
and
normal heap is like a heap. I mean, normal heap is like a list only, but yeah, updating a value. Anyone can answer this? Guys, I want your help in this. Min heap, Dijkastra is using a heap, Max-Heap, left child, right child, heap.
It's written there. There are two types of heap, right? There is nothing like normal heap.
Acha, okay. Is that the case? Okay. Okay. If you're considering it like a min heap or max heap, then yeah, that's correct. Am I right, Ma?
Yeah.
All right. So shall we go for the guys? Next question. Ignoring it as of now. Okay. So week 6, all the programming assignments, we'll do it later if we have time. I mean, programming questions. So shall we do with week 7? Finish it off. Week 7, we have done it already. Uma? Okay. Mahi?
Yeah.
Okay. What about others? Have you guys done these week answers? I mean, were you there for
We
these?
can do week 5.
You want to do week 5? Uma,
If
shall you
you
do that?
disagree.
Right. Anyhow,
It's
we
okay.
have. Sorry.
It's okay, but I think that will be heavily loaded.
Sorry.
Remember all the algorithm, no? It will take time.
Uh-huh. To recall, right? So if you are completing week 5 today, then we can start with the previous term questions in the next and next sessions.
Okay.
We can skip week 7 if you want, if you say, because we need at least 2 sessions to do the previous term question papers, right?
Yeah.
Mm-hmm. So coming here, so Floyd-Warshall algorithm. So we need to remember how the algorithms work here, right?
Yeah, there are a lot of algorithms, that's why.
Okay, fine. We have the Floyd-Warshall here. So what's Floyd-Warshall gonna do? It's all path. I mean, all path shortest path. Correct.
Yeah.
So we have this here. And how does Floyd-Warshall algorithm work? Hi, Afnan.
Yeah, hi Google. I've been, so see the previous sessions. I'm always late. I'm sorry for that, but then there are some other commitments which I have to, you know, attend to, and therefore I was not able to join in time.
It's okay. It's okay. Fine. Fine.
So what are we discussing today?
Now it's week 5. We are doing.
Okay, so revision, no?
Yeah, revision. Yes. From
Okay,
next session, we'll
sure.
do the previous term question papers.
Okay, okay. So this is Floyd-Warshall, I believe. Yeah.
Yeah.
Okay, sure. Go ahead. Okay.
Mhm. So one thing we can say is like, Uma, this is like we are trying to find out the shortest path, right?
Yeah.
Okay. And should we recall how Floyd-Warshall works here? Mm, okay. I don't think it's not going to take so much time, Uma. Let's just recall it fast. Okay. So we have the weighted matrix, right? And
Yeah.
for all the rows we are going to put infinity, right? All these values will be 641, 641. That's okay, right? Do we have a view for this? How to do that? Okay, that's fine. I'll come back here. Sorry for that. Okay. So and we are creating a numpy of zeros, and yeah, that's right. So for all the things we are going to give infinity. So you're okay with this, right? Until this point.
Yeah.
Hmm? Okay. So this is nothing but for I, j, k. If w mat of I comma j. Okay. So 0 to 1 I comma j. Okay.
Such a long algorithm we got to compare to that.
Mm-hmm.
Shall we just take the formula?
Okay, you're saying that we'll just take the formula.
Yeah, because this is actually updating Excel long procedure for
Uh-huh.
version
Okay,
among all the separate.
fine. So it's going to be like minimum of spk minus 1 I comma j, I comma k, and k comma j. Okay. How do we remember this here?
So okay, may I add something here,
Yeah, please.
if you wish?
Hmm.
Okay. So this min, what is it saying is basically, see, for SP of k minus 1, we have already a path, kind of a computed path, right, from I to j. So what we're essentially checking is that, there is assuming that there is a direct path from I to j, and that we're taking as the first argument for this min function, right? This min that is there, and
Okay.
then there's a comma. So then we are what we're doing is we are trying to break up the path, right? So
Hmm.
we're breaking up into I k and from k to j.
Hmm.
So then we are kind of adding because that I to k there's a cost involved, right? And
Okay.
then from k to j there is another cost.
Hmm.
Okay, so we are summing the cost there I to k and k to j and seeing if that gives us something which is smaller than the original path that we had.
Hmm.
Okay, so that is the idea.
Okay, we can say something like from 6 to 5, right?
Okay, let me see
So we
once.
can take 0 to 1 it's here.
You want to
0 to
because
1 has
zero, if
base
you
10.
take 0 to 1, then you have these
Yeah,
things.
yeah. Okay. See,
Then
0 to 1
0
we have 10,
Hmm.
and then okay. So would somebody else like to take this?
yeah 0 to 7, 7 to 6, but it is not keeping on. We need only 1, right?
What do you mean, Uma?
No, it is traveling through 2 nodes. We need just 1 node, right?
Yeah.
I to K,
So
K to J.
correct. So it will be like uh, so I mean, this has the shortest path of. I mean, to reach 6. What is the shortest path? It's going to be 9, right?
Yeah.
So you can consider it like 0 to. I mean 0, 1, and 6. Shortest path of 0 to 6,
Okay.
and then 6 to 1,
Okay.
right?
Yeah, that's correct.
Mm-hmm. So ij is 0, 1. Okay.
0 1.
0
Okay.
to 1. Okay. So ik is going to be 0 to 6. Shortest path of
6.
0
Right.
to 6 is going to
Right.
be 9.
9.
Okay.
Mhm.
Plus.
And then from k to 1, this is minus 4. So that is
Yeah.
giving us like 5. Right.
Huh. So 9 minus 4, which will be 5.
5. Correct. And then the other one that we had, that was 10. So
10.
obviously the the longer one is I mean like is smaller in terms of cost actually.
Correct. No,
Yeah.
bro. I mean the three different stops,
Mhm.
right?
Yeah, exactly. I mean like longer in the sense that it had more
More nodes.
connections, so to
Huh.
say.
Uma, okay?
Yeah.
Yeah, but one doubt of mine, like when I go to through in the exam, like this kind of graph is given.
Mhm.
So can I take it as two nodes in between also, right? 0 to 1.
Hmm. So, well, what Google is suggesting, I am also kind of agreeing with that. But then, algorithmically speaking, how does it take that previous one into account? Is something to do with the computation that we do.
Hmm.
But yeah, I mean,
This
as
is
an example, I think this one.
okay.
Right, this is taking care of the fact that we are coming from the
Yeah.
previous one also.
So 0 to 6
Uh,
is also considered. Okay.
Considered, yeah.
Okay. Yeah, thanks.
Okay, so basically what will happen is from 0, if you have a direct edge, okay, it will compute the shortest path. Uma. So
Yeah.
during the first iteration, 0 to 7 and 0 to 1 will be marked as the shortest path, right? And after that, everything will be, still will be remaining infinity. Okay, then you will calculate the shortest path from 0 to 6.
Yeah. Yeah. That
Okay,
will be yeah.
I mean that's how it's gonna happen. So for all the elements, how so from 0 to 6 it will be uh what 8 and 1, which is 9, but the rest of the things it will be like infinity or something like that.
Yeah.
Okay, so let's go to the next question here.
So, if you don't mind, Google, could you please just go into the initialization part for the infinity thing? I'm not able to still get the idea of what, how do we get that infinity to, that calculation only, that mathematical part of it. Why we are taking it as n max of w max, and then we're multiplying with rows, again with rows, and then adding one to it. So, what is the idea behind it? I'm not able to exactly, get hold of that.
Okay, the thing is, see, this value is gonna some, I mean, so according to this question, the value is coming
Yeah, I
as
mean, the
641.
infinity part is fine to me. Like we are initializing it to something which cannot occur, right? So
Correct.
just to say that that will be the maximum that cannot be reached. So then we are updating it with minimum, so
So what
that
is
we
the
will be
question?
getting. My question is why this one and not some other quantity? Like, what is the idea behind the formula that we're using there for infinity? How are we arriving at this number, and why so?
This is the smallest unreachable number.
Exactly. That is fine. But then how are we arriving at that formula? NP dot max of what it is giving actually. I'm not able to kind of
Max of
get
W
into it.
mat. Okay, this is max of W
Yeah.
mat. So
So I'll have to kind of think through it. What it is representing actually.
okay,
So
one second.
NP dot max is fine. Okay. So the W mat that we have the weighted matrix, we're
Correct.
taking the maximum of whatever inside of it is, right?
So
And
what is
then
it
we are
going to be?
so what yeah, exactly. So just take an example, then it will be easier. So for example, in this case it will be
Is it 10 here?
okay. It will be 10. Why is it so? And if we are taking max, then in which dimension we are taking it as?
The third one it is taking, I think.
All right. So how do we know that it is taking the third one?
Because I mean, obviously that's how I have seen it already. Okay,
Okay.
so
Okay, it's
basically
fine.
the
It's fine.
weight.
You can kind of skip over it also. That
Huh.
max part. Okay, assuming that we got 10 as the maximum,
Mm-hmm.
then we are multiplying it with rows, and then why we are doing so, right? Why
8 into 8 in this case, right?
in this case it will be 8 into 8 plus 1.
Huh.
Sorry. Yeah.
So 8 into 8, which is 64, into 10, which is 640, plus 1, which is
And it was
641.
641. So why this formula works? Like why it is safe to take it as infinity, right? I mean,
Huh,
why
I'll
not
tell you.
something else?
I'll tell you. So what is that max? That max is
Or
nothing but the
maybe yeah,
maximum
if you
weight.
wish you can kind of discuss it at the end also if it is taking so much
No,
time.
it's gonna take
But
me just 2 minutes.
2 minutes, it's fine. Okay, then I
Yeah.
don't want to
No. So we let's say we have some graph. Okay. So I'm just
okay,
gonna
all right.
have 1, 2,
Mhm.
3, 4.
But
Okay.
that I assume is kind of important to know also. That is
Yeah,
why
yeah.
I was
This is enough. Okay. This much is
yeah.
enough. And give me some weight. So shall we take
All
10?
right. 3, 10. Okay, yeah, it's fine. Larger weights, no? 8,
8,
maybe 3, smaller one.
3. Okay. So what's the maximum
Okay.
of these?
10.
Okay. What's the total number of nodes?
There'll be 4.
4. Okay. Into 4.
Mhm.
Nothing.
Again, for what it is like, what it is representing the other 4 also. I mean, why are we squaring it?
Basically,
Is-
it's like you're having a root from every places.
Okay, so we're kind of assuming that if it had been a connected graph in that
Yeah,
case.
if it had been like 1, 2,
Hmm.
3, 4, the same thing.
Hmm. All right.
Okay.
Okay.
So
Okay.
1 to 2 it was 10. Okay.
Hmm.
2 to 3 it was, how much was that? We have not given, but let's consider it as 8. Okay.
Oh, right. Okay.
Or else, what should I say? It's fine. Let me take it as 8. Okay. Then
Yeah,
3,
it's fine. Okay.
3 to 4 it's going to be 3. Okay. What is the shortest path to reach 4?
Well, there's only one path to, of course. So of course it will be like 21, I believe.
21. In this case, tell me the shortest path to reach 4.
Short part to reach 4. You're saying no? So it will be
Yeah.
10 plus whatever.
No. 8 plus 2, 8 plus 3. You can
Okay.
easily complete.
Okay. Going it with this path, no?
So
8
it's
plus 3
11.
is
The
11.
shortest path is 11.
Oh. Okay. Okay.
Here it is 8. Here it is 10. Right?
Okay.
Okay. In this case, it's going to be 10, and in this case, it is 18 here, and here it is 21. Correct?
Okay.
Okay.
Correct.
So why we are doing that is basically, so you take, for example, if it was 1, 2, 3, and 4. Okay. So everything was 10, 10, 10.
Correct.
Okay. It will sum up to 30.
Hmm.
Okay.
Correct. Correct.
And according to the infinity that we are going to take, all right.
Hmm.
So it could also be like, what do you call a click,
Hmm.
right?
Click.
So
Yeah.
what does the click mean? We have 4, and all
Hmm.
the 4 are interconnected. I'm not sure.
Interconnected.
But this,
Hmm.
like in this case, if you take 41 as 41, it is more than enough to say it is
More than
integer.
enough to say. Yeah, that is totally fine. But then,
Why it is like,
so I was, so my interpretation, I'll tell you my
yeah.
interpretation of that. So I was assuming that it will be taking the, weights for everything, right? So, and then kind of assuming that it will be connected, even though it is not, because then that will give us a larger number, which is fine, right? I mean, even if we go beyond 641, assuming, then
Hmm.
it will be fine, right? So what we're doing is basically whatever possible weights may be there, we're taking the maximum and then kind of multiplying, assuming that every, see what we're doing is basically we're taking 10, right? 10
Yeah.
and assigning
Yeah.
every weight to 10. We're kind of making it same for
Hmm.
everything, right? That is the maximum. So assuming that everything, takes 10 cost,
Yeah.
and then we are kind of doing that connected graph thing, right? N into n minus 1 kind of thing,
Hmm.
right? And then adding 1 to it, so that is the maximum possible that we can have, and then
Correct.
we're adding plus 1 to that, so that is kind of assured that we'll never reach that. So is
Correct.
that
Correct.
reasoning correct?
Yeah.
Okay. So in this case, in this graph that you have drawn, assuming that we got np dot max wmat as 10, then we can imagine 10 being spread out to every other weight that is there, right?
Yeah.
In this quantity that we are computing,
Hmm.
because that is maximum, right? Everything is less than that, so we're
Yeah.
taking the maximum and then we are multiplying, assuming that, kind of imagining it like a connected graph,
Yes.
and then computing what could be the maximum weight that that connected graph could have,
Hmm.
and then adding 1 to that,
Yeah.
so that we can never kind of reach that.
Correct.
Yeah, so had it been a click or had it been a fully connected graph, it would still be higher than that.
Maybe yes,
it,
or
sh-
may
it
not
should
be.
have, it should be, right? I mean,
See, if it's a click
because we are
means, then if it's a click means if everything is like 10, 10, 10, the shortest
Mhm.
path is going to be 10 always.
Okay. So then infinity is not making sense there.
Yeah. If it's a click, it's not making sense over there.
All right, understood.
Yeah.
Okay, so that was my kind of interpretation, but I was not able to get behind get the intuition as to what this mathematical formula is giving us.
Hmm. So shall we move
That
forward
quantity
now?
is whatever numbers we put, that is fine. Like, I mean, numbers could be anything. We are kind of multiplying rows into rows
Correct.
and whatever maximum we get. But why is that formula giving us the correct number? Is what my question is.
So did you get it or still no?
Okay, somewhat better, but then I'll have to through it once again. But it is fine. I mean, you can go ahead.
Yeah.
Maybe.
Okay. Let's move forward. Now
Yeah,
let's.
of course.
Yeah.
Sure. Thank you.
Uma.
Yeah.
Okay. So next question. So Kruskal's algorithm might produce a non-minimal spanning tree. and Kruskal's algorithm can be efficiently implemented using the disjoint set data structure. I don't know. Seems like, but Kruskal's algorithm, what is it used for? First thing.
And the minimum MST, right? Minimum spanning tree.
Exactly. Where do we have it here? Huh. We have the Kruskal's algorithm, and that algorithm is basically used to compute the minimum cost spanning tree, right? And so they were saying that what was the other one? Using what? Disjoint set data structure. Okay. So basically, this first option is wrong. That we can see, right?
Yeah.
So it will always produce the minimum cost spanning tree.
Yeah.
All right. And efficiently implemented using disjoint. Okay. Shall we recall Kruskal's algorithm? How does Kruskal's algorithm work? Do you know? Do you remember?
Yeah, it is just we are combining the components. Go.
Components. We just change the components values, right?
It is a kind of disjoint data structure, right? Some are they are not connected, so it
Correct.
is true.
Fine. Mahi, okay with that? Hello? Mahi, are you here?
Yeah. Yeah.
Okay. What is a disjoint data set?
According to me, I don't know I'm correct. We have a set of data, right? Some are connected to some components, and half of the connected to other components.
Correct.
And at the end only we are going to connect it, right?
Mm-hmm.
I don't know whether it is true.
Yeah, that's how we used to find out, right?
Yeah.
We
So
change the
that is
component value.
called as a disjoint data structure. I'm not sure what they mean. In Kruskal, that's what happens.
Okay. Fine. So shall we go to the next one and go to the good ones, basically? Okay.
So, just to add to the previous one, actually, Kruskal or Prim, one of them actually, what it does is basically picks out the, kind of disregard the graph completely. I mean, for the time being, and then kind of look at the edges that are there, and then we kind of start picking the minimum ones so as to keep them connected.
Correct.
And whenever we form a cycle, right, we pick a node, we pick a edge basically, and then we see that okay, we are connecting this to this, and that is forming a cycle. And then if we are forming a cycle, then we kind of skip that one, right? If it is not forming a cycle, then we'll pick that one. So uh, you know given the fact that we are always choosing the minimum one among the left that are left, so that overall is kind of giving us the minimum that is possible while keeping the tree connected. So that is the definition of MCST as well. But then Prim's working is slightly different. I think it works with the uh, paths and something like that. Kind of similar, but then yeah, Kruskal's I think that is easier because of the fact that they are just kind of. I always imagine it like that. So kind of picking up the edges.
According to the question, Prim's is not disconnected, disjoint, right? Prim's joins the continuity is there, but in Kruskal you can randomly
Yeah,
change anything, any
yeah,
component.
minimum. Exactly. So it is like we have the graph, but without the edges, right? So we kind of picture it like that. So we have the graph, and then we kind of remove all the edges and start picking minimum ones
Yeah.
and keep connecting them. So that is what the components connection is kind of
Okay.
giving us.
Yeah, that's right.
But then in Prims, I think things are connected. So this is not like disjoint
Then
thing.
it is we have to choose from the adjacents, right?
Correct.
Adjacent ones.
You can't go further beyond that disconnected one.
Yeah.
Kind of like the Dijkstra's thing, right? Dijkstra maybe.
Yeah, next. So among that connected ones, we have to choose them.
Mm-hmm.
What does disjoint mean here?
Repeat.
What does disjoint mean here?
Okay. Fine. I'll just take this graph. Okay. So consider that. I mean, ignore the orange things, but consider that it is a graph. Okay. So for this graph, if you want to find out the MCST, how do you find it out? There are two ways, right? One is Prim's and another is Kruskal's. Right, Mahi?
Yeah.
Okay. In Prim's, what do? First, you take the edge with So will we have a short source vertex, right? I mean, is that how it works here, guys? Afnan?
Yeah, so I think we'll start with the vertex and then keep on seeing whichever is giving us the minimum among the possible routes that we can
Correct.
follow.
Okay, we start with 0. That means, from 0 we take the lowest one, right?
Mhm.
So we come here, right? So what's next here?
It's 9. 4.
Okay. Okay, wait, let's just look at the visualization only. I'm just not okay. So Prim's algorithm, and the source I'm going to make it as 0. Okay. So starting from 0, so you have two ways, right? So you're taking the smallest one. Okay. So you go to 1 and then you take the smallest. So which is 9 here, right? So the next smallest is 12. Okay. Then the next smallest is 13, but it's forming a cycle. You don't go there and you go to 14, right? So since this also is visited, so all the other edges connected with 13 you will do it, and whatever is the minimum among the edges you will connect with that. Got it?
Yeah.
Okay. So if you take this, it's going to form a cycle, so you don't do that. So you take the next. That's how. So see, in this case, every time you pick a new vertex, it's going to be connected, right? This is joint, and if you go to Kruskal's algorithm, um, okay, so this is the minimum, this is the next minimum, and see, this is 9 is
Yeah,
the next
we're
next
not
minimum.
following the. Yeah, we're not following, right? We're just picking,
Exactly.
Yeah. It's
edges
two sets now.
arbitrarily.
At
Yeah.
this point, it is disjoint and it is two sets, right?
Correct.
Mm-hmm.
Yeah.
Okay, now you understand why it is disjoint.
Yeah, now got it.
Assuming that we pick the edge that connects from 0 to 1, so we got one, component, and then we pick 3 to 5, so we got another component. But then
Correct.
eventually, we keep on doing this. Eventually, we'll have something that it's connected, right? To
Mhm.
incomplete. So then we'll have the MCST that gives us the answer.
Correct. So that's why Kruskal's algorithm is using a disjoint data set data structure.
So this statement 2, is it also true for the Prim's one? I think so, maybe not, or
No,
maybe
it
No,
is
no.
not true.
it is not true, no, because we are strictly following the
Yeah,
path that
it
we are
is
giving.
not
Yeah.
at all disjoint. Yeah.
Not at all, just join. Yeah, correct. Okay, thank you.
Okay. So this is an interesting question here. So the graph shown below has 8 edges with distinct integer weight. So distinct. So they are not repeated. Okay. So X, Y, Z. The red edges represent the minimum spanning tree for the graph. What minimum possible value can be assigned to X, Y, Z in the graph without changing the minimum spanning tree? So we already have the spanning tree. Okay. So and how they given the options? Yeah. So these are all the options. Okay. So if we put some value, okay. Um. Yeah. Mahi, did you understand the question?
The red lines are minimum spanning trees. That's
Correct.
so.
Red line is the minimum cost spanning tree.
So we should put XYZ in such a way that it doesn't affect the red line. Is that the
Correct.
question?
Correct. So which means X should be greater than 219, right? Because
Yeah,
it's
yeah,
forming a
that's what I
cycle.
was. So all we have to choose the largest numbers, right?
Correct. So if you put 7 here, then it will change that from. I mean, it will change it, right?
Yeah. So 10 is the best.
So
Yeah.
so X is going to be 10.
10.
Mahi, are you able to follow?
Yeah.
So we eliminate these two options. Okay. Now we have Y equal to 7, 16, 16, 7. So for Y and Z. Okay. So we have to. How do we find this? So Z should be greater than 4 and 6. That's one thing, right? And
Yeah.
also Y should be greater than, I mean, where is the next cycle forming for Y? So 2, 15, and the Z is also coming up in between. I'm not sure. But 6 and 4 you have. So it should be greater than all these 4, right? 2, 15, 6, and 4. So ideally, Y will take the value of 16 and Z will take the value of 7. Am I right or wrong? Y will take the value of 16, correct.
Yeah. Can you repeat it? Why value? I'm not getting it.
Yeah, Uma. So, you see, we have, so this and this.
So if I put Y as a 7, it will pick BD and BC, right? It won't pick BA. That's what
Correct,
your point?
correct.
Okay. Yeah.
Okay. So that's why it might change. Got it?
So is there any assumption about the algorithm being used, or it is a general case?
You can assume some algorithms also, Kruskals or whatever. What do you mean?
So it is valid for both. I
Huh.
think.
Kruskal and
Yeah,
Prims
because
both
it
are
is
valid.
about the structure of the MCST only, and not about the algorithm being used to compute
Huh.
that.
Correct.
Correct. Okay. Sure.
Hmm. Probably we'll have some more questions like this in the previous term question papers. So when we do those things, then we'll be able to do that. Okay. And this is basically there are multiple shortest path from S to T. Which of the following path will consider as the shortest path given by Dijkstra's algorithm? So from S to T, copying the image. Okay, but it's based on the
So
code
this,
given.
I think, the tie breaking is. Sorry to interrupt, Google.
Yeah, yeah.
Please continue.
No. Finish it off.
Yeah, so I was saying that since the tie breaking is happening based on the min function, is what I can see here. In line number 13, we have the next v, which is the minimum of the next v list. So all the possible, routes that we can follow, all the possible vertices that we can go to, we are taking the next one to be the minimum among
Yeah.
those, right? And
Correct.
then since the, that numbering or keys are basically based on the alphabets.
Mhm.
So what we can assume is that whichever alphabet comes first, that will be taken as the whichever letter comes first, that will be taken as the minimum, same as number, right? So if you have 1 2 3, then 1 2 3, like that. So similarly for abcd, you'll have minimum as whatever is coming before the others. So for example, acd, you'll take minimum of acd, you'll get a, right, like that. So in this case, I think whatever path that we will get, will have the minimum ordering uh, in the path. So it is like, so you can just possibly see in the options and see, whatever is following that minimum order, that I think is a possible choice that we can make, because it is same, right? Assume they are numbers only, right? So then how do we do that? Similarly for letters also.
Okay. So from S to T, right? Basically.
Possibly if you have the options also, that will be helpful. So uh, I think first of all, you'll have to see what all paths are the minimum paths, and then among those you'll have to, because it is said that there are multiple shortest paths. So we'll have to find out those, and then from them we'll have to just see the orderings, right? So
Yeah.
whichever ordering is following the correct order, that will be in the minimum order, that will be taken as the path.
Anyhow,
So
it's going to be one of the four.
of course, yeah, that is the benefit that we get in MCQ.
Huh.
Yeah.
Okay. Uma.
Yeah.
Okay. So SBDT. Can you tell me the weight of this?
Yeah. 3 plus 4 plus 3, right?
Which is 10. Right. Then SDT.
7 plus 5.
7 plus 3. SDT na.
Oh, DT. Okay.
Okay. Then SACGT. Yes.
4 plus 1 plus
Mm-hmm.
E. Where is E? Okay. 1 plus 4. So, okay.
10.
5, 6, 10. Yeah.
Mm-hmm.
SACPT. So I think it is going to be 10. That but like, not.
Yeah, that is the thing. So once we have the path, so assuming so it appears that all of the paths are possible paths, then the tie breaking is happening based on minimum. So we just have to see the later orders. So
Yeah.
we
So you
have
have
this,
to go for the last two options, right? Because of
but
S.
then yeah, it is possible, but then you'll have to kind of follow through, right? Follow through it. So we're going to S, and then after S we are going to B or to D, right? Or to A. B, D, or A. So among B, D, and A, because after S, B, D, and A are the possible things that we can
Correct.
choose. So among B, D, and A, there is A which is minimum, right?
Hmm.
Among according to that tie breaking thing. So S A. So we have this two vertices there.
See, Uma. Next V is the minimum of the next V list. Next V list is
Hmm.
A, B, and D, right?
Yeah,
Okay, and
from
you're
S.
taking the minimum of them,
Correct,
which is
correct.
A. Okay, then
A,
you come to
and then
C.
from A we are only going to C. So there is nothing to check here, of course.
Correct.
I mean, because we are just going to see, so that is okay.
No, can you go back? We are taking the minimum of A, B, D only, right?
A, B, D. Correct.
B is 3. Is it not 3?
What is D3? How come you're saying D is 3?
S to B. Right?
A, B, and D, we are taking characters.
Okay.
Okay, A, B, and C, not the weights or not the length.
Okay. Yeah.
Hmm.
See, because the overall cost is anyway going to 10. That is something that we have already calculated.
Yeah,
So
yeah. So we're going for that. Okay.
Mm-hmm.
this is just about the tie breaking thing only.
Yeah. So we come
Yeah.
here after this.
So from C we can see that SAC we are at C, and then we have two options left, E or D, right?
Mm-hmm.
So of course you have to take D because that is the
E.
minimum
Okay.
because
Yeah.
D comes before E. That is what.
Yeah.
Mm-hmm.
Okay. So the last option should be correct if the no
No.
something is wrong there also.
Exactly.
Okay. Why is it so?
That's why this question is an interesting question.
Hmm. So is SACET giving us a different weight, or is it
No,
a
no,
10
it's giving the
also?
same weight. It's giving the same weight.
Then
You don't need to worry about that.
so from C the problem arises, right? So from C,
Mm-hmm.
if we go to D, then that is 2. If we go to E, then that is C. From C, if we go to D, that is 2, and if we go to E, that we can see that it is 1. So obviously we get to select E, no, according to the weight.
If you're saying that according to the weight, then it should go to B, right? In this case, while starting.
Yeah, that is also a correct assumption. Mm, okay, there is something tricky here. Then I was thinking that it is just a,
Okay.
Maybe they have given wrong. We'll check in this course. We'll ask.
but the minimum, that code is the same. I believe that the same code that we also use in that, we have the
Correct.
vertices. If we have numbered vertices, 0, 1, 2, 3, like that, then also we do the same thing, no? So it is something to do with the visited, I believe, because then next we do not have. It appears that from C we do not have D at all in the next V thing, because there is this assumption that we can take D and E both. But I think at that point, when the algorithm is at that point at C, so in this case, when we run this on this graph, what is happening is that D is not at all in the next V list. So that is why, you know, I think that is only going to E, but then we'll have to, run through it and see why it is so. That is one possibility that I'm able to kind of get,
Okay.
right? Because see, you may have multiple paths, but it is not necessary that you'll follow them, right? I mean, you have them in the next V list, because there is this condition also, if not visited of V, it may perhaps have occurred that D is already visited, right, at that point when we reach C, and hence we are going to E only. No, that is something that might be possible, but I'm not very sure of that.
Okay. So this is Dijkstra's algorithm, right?
Maybe we can run this on this. Okay, this graph is a complicated one, so
Yeah. So this is a Dijkstra's algorithm. So at the third minute, we are at this point, right? So the visited is going to be only 3. Am I right? At the
mm,
third minute. Okay. So
yes.
at the fourth minute, you have B and A, right? At the
Yeah.
fifth minute, you have B, A, C.
All right. Visited, no?
Yeah, visited,
Correct.
right? So at the sixth minute, tell me what or how much are visited? B, A, C, and E also will be visited, right? Only at the seventh minute you are going to visit D. See
Mm,
this,
mm, yeah.
okay? Distance, like you
Mhm.
can say like seventh minute or seventh kilometer, whatever.
Yeah, yeah. Understood. Understood.
Okay, so see if not visited, so there's this condition. See,
Mhm,
distance of V for V in range of rows if
mhm,
not
mhm.
visited. So if it's
Yeah,
not
correct. Correct.
it not visited, all these things it will check and then it will check for this point. For sixth minute, it is gonna come. So this is gonna get included into the visited dictionary.
No, not yet. No, because we're just computing the next D. We're just getting the distance and not the actual vertex. Sorry, the actual vertex. The actual vertex we are getting it only in the line number 13. No, because this list we are computing. So I was saying that in the list also we have this condition, no, if not visited of v.
That's
So what I
correct.
was saying is, that perhaps D at that time was visited, and hence it was not included in the next v list, and hence that option was kind of eliminated at that point. Because see, minimum we don't have any other choice. Yeah, please continue.
No, just check the answer. They have given feedback. Can you check?
No, for us, it's not given here.
Okay, it is given something connected to the parent
Repeat.
to trace back. That is the feedback. I just checked it.
Okay.
Shall I read it?
Yeah, read it.
Use its feedback using this parent information in the dictionary parent. Do we have that? Okay, Gokul, your thing it is not given. For our code, the code is corrected. They are also giving the parent information.
Okay.
So using this parent information in the dictionary parent, we can find the path in reverse order from the destination to the source using the parent vertex of each vertex. Hence, SACT is the correct answer. Maybe the clue missing in yours, they have given in our code.
Mm-hmm.
All
We
right. So
have
they're
parent
saying,
out.
okay, so they're saying that we are tracing the parents and getting the path that it followed, right?
Yeah,
Algorithm.
yeah. So this is the only choice which allows to trace back.
That is correct, but then the algorithm could as well follow SACDT, no? Because I mean, algorithmically speaking, that is also a shortest path, no? Because that is also giving us 10. So I thought the question is more about why it went through SACET and not the other one.
For our codes, they have added the parent or information
Parent,
also.
okay, parent is not there, then there might be something
Yeah,
related
for
to that.
Gokul's one, yeah, later they
Yeah.
have. It's a mistake, like we can't find it. No, now that's it.
Yeah,
Okay.
possibly.
Fine. Let's continue. This, I think, one last question is here. What is the weight of the minimum spanning tree for the given graph? We come here. So how do we do that? We can take the what algorithm we can take? Kruskal's? Easy, right?
Prims maybe.
Uh, like Kruskal's or Prince, whatever.
Yeah. I mean, I just thought that it will be a kind of a nice
Okay.
recap
So
also.
let's
How
go with
Prims.
Prince. Let's go with Prince. I'm gonna start with F.
Kruskal,
Okay.
I think, is easy. So yeah.
It's easy, but Prince will go. Okay. So we
Okay.
are
Okay.
starting with F. So F has got like 4, 2, 4, and 10. There are 4 edges. So we take the minimum edge, right?
Correct.
So it is going to be 2, right? Now we have B here. Okay.
B.
So now we have 4, 10. This 4 is also there, and B is connected with 6, right? So 4, 10, 4, 6. So we could take any of these, I mean, whatever, like this 4 or this 4. So let's take the left one. All right.
Okay.
Mm-hmm. So C, and we are taking it 4. Now C is connected with the D, and with weight of 7.
Gokul, that FB is also there. Is it not? FB2.
I have put it here already. Now that we have already
Okay.
marked it, no? That's why I did not
Sorry.
put it. Yeah. So if I'm doing that, I'll just erase it. So we don't want to see it anymore. All right. Yeah. So where were we? Yeah. So we have connected C, and C and D. If you are okay, we can do that. So which is of weight 7, and C and A is connected with weight 2. Am I right?
Yeah, you can choose a C and A, right?
Now we are going to choose C and A because it's having weight of 2. I'm gonna put it like this, and 2. So now that A is also visited, right? All the okay. Now that's all. Like A don't have anything else new here, right? So this is gone, and A, B, C, only D is left, right? So we can see that,
Important, right?
yeah, from F to D it is 4, right? So we can take that F to D, can put it as 4. Okay. So what's the cost here?
No, D to E.
Acha, one more thing is there, right? D to
Yeah,
E.
we need all the letters. No? D to E.
Yeah,
Yeah.
yeah. I don't see that. Yeah, 7. 8 plus 7 is 15. 19. Is it 19? Answer? Yeah. I think I confused everyone.
No, you're doing good. Correct.
No, got it.
Okay.
It's clear. It's clear.
Yeah. So that's how the Prim's algorithm works.
Mhm.
So let's do the same thing with Kruskals. Okay. How do we do with Kruskals? It's gonna be
That
CD
is
first.
easier way. CF, CA,
Oh, so wait, not CD, right? It's not CF, and it's CA first, right?
F, FB is there.
Correct. And we have this FB, B, and F, which is of size 2. Okay. So what's the next one?
FD,
FC we don't want to correct, so FD will go. Yeah, it's 4. Then what's the next smallest? It's BA. And BA is already, I mean, A is already discovered. A, B, C, D, everything is discovered. Only E is left. For E, we have two edges, which is 10 and 7. So we'll take the 7, right? Again, so 7 plus 4 plus 2 plus, oh, what is this? I don't know.
C
Let me
is
see
2.
something.
FB is 2. Yeah.
Yeah. I think we missed connecting A and B or something. Because you see, at this point, C and A is
Yeah,
disconnected. Uma,
yeah, correct. B and
yeah,
A we left it.
correct. So
6.
it should be BA. Yeah, that's the thing, right? So 10, 10 plus 7. Wait a minute. I think we are gone somewhere wrong. I am wrong there. So we'll do it again. Guys, please help me.
Let's start from FB.
C to 8 is 2. Okay. And FB, we have 2, right? So what's next?
Should select one of the 4. Now you go by the graph itself so that you can correct easily.
Mm-hmm. We can go to FB also. Right? I mean, sorry. Yeah,
Now what I'm
FB.
saying is you draw as such in the image so that it will not confuse us.
What do you want
FB.
me to do? So we choose these two.
If FB is crossing CB, no, that's what I'm telling. CA.
FB is crossing CA.
So that will be easy for us to trace it.
No, let's not do that because it's confusing.
Okay.
So now we can take
So
this
I think we are
FC.
going good now. So okay, it's fine. I think we are going right. So FB we have 2, and then we have taken 2. So there was this another 2, right? C to A.
Hmm.
We took that 2 also, and then among the minimum we have 2 fours possible, right? FC or FD. So let's go with FC first.
Huh?
Yeah, we have taken FC and then FD also because we have to connect them, right?
Correct.
We cannot kind of keep it
Yes.
isolated. So that is FD.
Now it's correct.
Yeah.
So now see,
What's left now?
that's all.
That's all. Huh? Yeah.
Yeah.
Just sum it up and what we're getting.
Yeah, 19 we are getting.
19 we are getting.
So what
Okay.
is the mistake we did last time?
Uh, I mean, the graph that I drew was like it was confusing for me. I thought like,
Okay.
yeah, so that's why I thought like it was connected already, but it was not connected.
So B to A, we are not taking that edge, no,
Correct.
this time.
Yeah, we are not.
Mm. Because B is connected to the whole graph through F.
Hmm.
And how A is connected? A is connected through C.
C.
So B to A is again not required because it is already there.
Yeah.
Yeah, the only objective, in this MCST is to kind of make sure that everything is included, nothing is left out.
Correct.
And the paths the edges that we pick are the minimum ones. That's all. Okay, correct.
Yeah, that's done. Let me
I
see if
thought
any.
that was easy, but that created even mistakes, no?
Yeah, right, right.
Okay. I'm not sure about the graded one. We won't be able to do it as of now. So from tomorrow, like we'll have 2 more sessions, which is tomorrow and day after tomorrow. I'll